Okay, so this is a course. This is a course about geometry and deep learning theory. I want to start with a bit of an apology for anybody who joined the class the week before the opening workshop for this program. I'm going to try to make this part of the course somewhat self-contained, so there will be a little bit of repetition, and hopefully it won't bore those people that came to that first week too much. And I promise to those people that I will be saying something new that you haven't heard today. Okay, so I just want to set the scene. I'm going to start high up and sort of zoom in thematically. Okay, so we're talking about supervised learning. So let me remind you kind of basically what we're doing when we do sort of supervised learning from a point of view. So at every supervised learning task starts with some data, and that data comes in the form of input-output pairs. And say you have M input-output pairs, and these input-output pairs are in Euclidean spaces. So you're thinking of your data as already having been embedded somehow. Your data has already been embedded somehow into some Euclidean space. And the idea, so this is called the input space. And the idea is that this is just a finite data set from some unknown probability distribution. So I just want to say that at the outset. Give it a name. And we'll see in a moment why I'm using this particular notation. Okay, and then the idea is that we want to somehow learn the outputs from the inputs, but on other data that's drawn from this distribution. So the way that this is typically done is that you choose, first of all, a parameterized function class. This is like your bag of functions from which you're drawing to find a function that predicts the output from the input. So you can think of this as being a set of functions as theta, Rn0 to Rn. Theta is in some parameter space, some Euclidean space. So this will be my notation for parameter space, capital omega. So this is a parameterized function class. And then you're also picking some particular objective. So in this case, or typically what you do is you define some loss or error function. And so appropriate loss error function. And I'm going to be clear that this, so typically people say empirical loss or error function because it depends on this data that you've chosen. Okay, so this is now a function, which we'll call L sub D, from your parameter space to the real numbers. Okay, and the idea is that what we're trying to do is from this bag of functions, we're trying to minimize this empirical loss over this parameter space. Okay, and this can come in various forms, but let me just be quite general for now. So what you're trying to do, you're trying to find the particular parameter that minimizes this empirical loss. And typically you use an optimization algorithm. Typically gradient descent, some version of gradient descent. So you can imagine graphing this function. I'm just going to draw a cartoon. You have your parameter space down here. This is a function to R, you graph it, and you're looking for some kind of global minimum. And the way that gradient descent works is that you start somewhere and you just start stepping in the direction of the negative gradient with certain step size, and you hopefully arrive at some nice global minimum. Hopefully. Okay, so and then at the end, what you're trying to do is argue or empirically verify in some way that this function that you found via this optimization algorithm generalizes well to unseen data. So you don't want to just learn the function on a particular data set that you've drawn from this unknown probability distribution. You want it to predict well on data that it hasn't seen, drawn from that same distribution. So drawn from this probability distribution. Okay, so the way that this is typically said is that the empirical, you want the empirical risk minimizer close to the true risk minimizer. I won't be more precise about that for now, but.
Am I supposed to picture that the probability distribution is concentrated near the graph of a function? That's the function we're trying to find.
Yeah, that would be, I guess, the hope, but really you want that graph to be kind of like the average over the possible outputs. But yeah, you're kind of allowing that joint distribution to be kind of anything. So you can't necessarily guarantee even that the outputs are kind of close to the graph of a function. Yeah. Any other? Yeah.
The loss function is empirical by itself, or it's just a minimization process that is.
So yeah, I'm calling this the empirical loss function because it depends on the data. Yeah. But of course it's based on some kind of point by point loss.
But we decide in advance about the loss function.
Yeah, we decide in advance.
That's not empirical.
Right.
If we decide that it's
the choice of the loss function is not empirical, but when you actually do the optimization, it depends on the data. Okay. Okay, great. So that's the sort of 5-minute summary of supervised learning. And it kind of everything is a variant of this in a certain way, in a certain sense. Okay, so what I'm going to talk about in this course is particular types of parameterized function classes. So in this course, F will be a parameterized function class. neural network functions of various architectures, of some architecture. So because they're new and interesting, I'm going to try to tell you about transformers, and also because I want to understand them better. So my kind of bigger goal, at least for this part of the course, is to explore the geometry of the transformer architecture. The transformers are the architecture that large language models are built on. Because I know them well, and because they're actually part of the transformer architecture, I'm going to start by telling you about vanilla feed-forward neural networks. So I'll start with vanilla feed-forward. So let me, before I actually tell you really anything concrete and precise, I think it's always nice to sort of set the stage by pointing out some themes. So I guess I'll start with a mantra, which is kind of my personal mantra for the things that I've thought about, which is that geometry matters when you're studying these parameterized function classes. And also combinatorial toy models are very helpful. Okay, so geometry and combinatorics matter when studying these types of problems. So I'll draw kind of a schematic of the kinds of problems we're thinking about. So, I mean, you have this kind of family of functions, but they're divided into a bunch of different types. I talked about this transformer architecture. I talked about this vanilla feed-forward architecture. Somehow you're putting together these different types. And when you do that, you're choosing your model for the learning problem. And then on the other hand, you have data representations. So when you're doing that, when you're representing your data, and somehow the structure of these parameterized function classes, at least heuristically, it's kind of, at least the way people talk about it, it's learning new representations of your data. And that's somehow what you're doing as you're moving through the network. Okay. And here geometry matters, and here geometry matters, and they interact. And then there's sort of the question of interpretability. What is the model doing? And I'll say neural network models are largely, at least as I understand it, and I may have missed, somehow I think the difficulty with working in this area is that it's easy to miss what's happening in parts of the area that you don't have access to. So maybe I've missed some things, but my understanding is that neural network models are pretty much still black box models. So they give great answers. Experimental, you can run a model and learn something, but you don't necessarily, the model's not going to tell you how it learned it. The model's not going to tell you how it did what it did. You can look at the parameters of the model at the end, and the parameters are just going to be a list of numbers. So that's not helpful if you want kind of an understanding of what the model is doing. Okay, so this is kind of, there's just a lot here. So maybe I won't list all the things, maybe I'll just kind of say them out loud. So, so in particular, there are geometric biases in data representation and optimization algorithms. So if you were at the opening workshop last week, Boris Hannon gave a great overview talk about the theory of deep learning that I encourage all of you to go and watch the video if you missed it. But the point is, parameter space is not the same thing as function space. And things like empirical loss depend only on the functions. So we're kind of very familiar with this from, if we're mathematicians, we're interested in studying like moduli spaces. You kind of mod out by some sort of equivalence, and then you study that quotient object. Well, the quotient object for these classes is quite interesting, and not very well understood. But training happens in parameter space. So understanding what that quotient map looks like is important if you're trying to understand, trying to understand what functions are more prevalent than other functions in that space, more or less prevalent than others. There are also some well-known distortion, like geometric distortion effects for the data for different architectures, even in the feed-forward case, that somehow as you move through a network, the data is distorted in some well-known ways. So I'll try to say some things about that. And in terms of neural networks as computational models, so I mentioned combinatorics. So one of the very first things that people kind of want to do when they, or wanted to do when they started studying neural networks is construct discrete models of the computations that were happening. And that ends up being really important, for example, for interpretability. Okay. All right, maybe I'll move on because I do actually want to tell you some precise things and not just generalities. But please stop me at any point if you have questions. Yeah, sure.
Because I do have a question, but only if you want to talk about this now, maybe you want to talk about it later as you're overviewing. Like I didn't quite follow. Of course, like my ears perked up when you saw the comparison with moduli spaces, but like, are you saying there's some natural notion of equivalent on sets of parameters? Is that's what you mean by?
Well, yeah, two parameters are the same if they give you the same function, or are considered equivalent if they give you the same function.
I see. Okay. So
And
parameter space.
I mean, yeah, we're sort of like very, very used to thinking of parameter spaces like parameter spaces of polynomial classes. And in that case, if you have two different parameters, you have two different polynomials. In these classes, it is not that. In fact, there are positive dimensional spaces of symmetries, and that those positive dimensional spaces are inhomogeneous as you move through parameter space. So the dimension of the space of symmetries is different as you move through parameter space. Okay. All right. Okay, so let me now just describe a function class. So here's a function class. So here's the class of vanilla feed-forward neural networks with relu activation. So I'm describing F. Forward neural networks. Relu activation. So this is a function class that is, so it's a class of functions from Rn0, Rnd, that's realized as a composition of maps of a very particular type. So each of these maps is called a neural network layer map. And it's these layer maps that are easy to describe. So they're nothing other than, so for each FL, it's just an affine linear map. So a linear transformation plus a shift composed with a component-wise activation function. So this is component-wise application of an activation function. And I'll say some more things about this in a second. So an activation function is just a function from R to R. And the idea is that this is supposed to model whether or not or how a neuron fires. So maybe I should actually draw a picture. I should actually draw a picture. And so here this would be representing the neurons of a neural network of architecture 3221. And the idea is that you're sort of mapping from R3 to R2 using an affine linear transformation. And then each of the outputs, you're applying some activation function. So you're thinking of the components of the output as being the output neurons, and then how they fire is determined by that activation function.
Can I ask a very question?
Please.
Is there a reason why a neural network should work better than other type of functions, other than like the intuition that we want to mimic the brain?
Do I have a good answer for that question? I mean, so I think that people in the audience might have a better answer to this than I do, but I guess the way that I think about it is that people like linear functions, they're easy. And it's nice to just kind of be able to make things be linear mostly, but be able to apply some nonlinear function that you kind of understand pretty well. If anybody in the audience has a better answer to that question than I just gave.
It's also dense in the space of continuity with the number of layers.
Right, so yeah, you want the function class that you choose to be sufficiently complex that it can represent the functions that you need it to represent, and they're, yeah.
But that doesn't have to be neural network.
No, it doesn't have to be a neural network, but I mean, I think maybe the other thing that I would say is that it very nicely has these computational units and interactions between the computational units. So it's also kind of an algebraic gadget, because it's like you've got these tinker toys and you're putting them together in a particular way. So I think people like that. And also it seems to be a model for how the brain works. Yeah. All right, so, okay, so the point is that you have these maps where you first apply an affine linear transformation, and then component-wise you apply this nonlinearity. So the typical choice these days, the typical standard choice, and I guess it's always possible this may change, but is this function called relu. So this function, the way it treats activating neurons is that if the input, right, so sorry. If the component of the output is negative, it just sets it to 0. And if it's positive, it keeps it. So it's the 0 function, the identity function.
Why is it called relu? That's the.
Stands for rectified linear unit, and I don't know why it's called a rectified linear unit. So just a little bit of terminology. So when I talk about the architecture of a feed-forward neural network, all I'm talking about is the list of dimensions, the layers. So this is the input layer dimension, and then you have an output layer dimension, and then you have all the hidden layer dimensions. And it's a map that is a composition of maps through those layers. And D is the depth of the network. And the width of the network is kind of the maximum dimension of the layers. So width of the network is just the map, maps over the NIs. And then maybe I'll also say, so I said that this is a parameterized function class. Well, what are the parameters? So you have these affine linear maps. This is the ELF layer map, the ELF affine linear map associated to the ELF layer map. And this is, so you multiply by a matrix and then you add a vector. So this is and so the parameters of this parameterized function class are all of the entries of these matrices and vectors. So theta, you kind of unroll this in some suitable way. So omega is just R to the D equal to, well, you can check my work here. Okay, so it's just, yeah, you just count the dimensions of all these matrices. And this is the dimension of the parameter space. Okay. So I want to tell you, I want to get started by thinking a little bit about the geometry of ReLU networks.
When you were talking before, I think about discrete toys versions of this. Does the discreteness refer to the fact that we're not working in R n anymore, or is it referring to how the data is represented, or not even?
I mean, I think you can discretize a lot of things. I'll be giving an example in a moment about how to discretize ReLU networks in kind of a natural way. But sometimes discretizing data also is helpful. It's a great question. So yeah, let's, since actually somehow you perfectly set me up, Sophia, to write down the kind of introduction to what I'd like to do next. Okay, so let's just kind of get a little bit of a handle on. So it may not be surprising to you that any ReLU neural network function, so a function that can be represented in this way, is piecewise linear with finitely many pieces. Okay. In fact, one of the like classical theorems in the subject is that every piecewise linear function with finitely many pieces can be represented by a ReLU neural network. But let's kind of not prove that or anything for now. Let's instead just kind of try to get our hands on what these, how we might understand a ReLU neural network function as a piecewise linear function. Okay, so let's start with a single layer map. So typically what people do again is kind of record the components with these circles, which are neurons, and you can imagine these being variables, and then recording the parameters of the network by recording weights and biases. So you have this sort of extra node, which is going to be able to record biases, where you always put a 1 inside there. So we're kind of separating out the part that is linear with the part that is affine. So you can imagine there's always a 1 here, and then it's just a linear map on a space that is 1 higher dimensional. So here's this sort of augmented computational graph for this layer map. And the way that it's, you then start recording these biases. Should have color coded this. And then also the weights on the edges. So these are the entries of the matrix. Okay, so let me actually do some color coding here. Match what I did in my notes. So suppose you had, you had some parameters on here. Then what would you get in the input space? Very naturally, well, you get a hyperplane arrangement. And why does this hyperplane arrangement come up naturally? Well, this is just, say this is associated to the first output, the second output neuron, and the third output neuron. And this is just the boundary in input space between where this neuron is on versus off, where the ReLU is active and the ReLU is inactive. And also these hyperplane arrangements come with co-orientations, which point in the direction where the neuron is on. So from this, very naturally, you have a coding of the regions of this hyperplane arrangement by binary tuples. So in here, all the neurons are on. So I'll record that as plus, plus, plus. Here, let's see, to go from here to here, you turn the second neuron off. And you can go on that way and write down binary tuples for all the regions. Okay, and what you know, so this is a discretization of this neural network. And in essence, what we're doing is replacing the ReLU activation with just the sign. So you can. Instead of relu, you use the sign function. Here your activation function. It's just. Not gonna fly. Then the outputs are exactly what I wrote down here. Where plus here means +1. Minus 1. And I guess what I want to point out as kind of a first place where discretization helps you understand the geometry is that if you look at the corresponding output of the corresponding relu layer map. Well, just from what we know about relu, that it always its output is always non-negative. You know that it's that the output of this layer map is going to be in the non-negative orthant of R3. And in fact, the face of the non-negative orthant that a region hits is determined by that so-called activation pattern. So these binary tuples that I wrote down here, these are what are often called activation patterns. So for a particular parameter, you have a collection of activation patterns that are present for the output neurons. You can kind of see how it works. I won't fill in all the details, but this triangle in the middle maps to a triangle. It's not exactly the same triangle because it's a linear map, but maps to some triangle. And then this region maps to a two-dimensional face of the non-negative orthant, one-dimensional face, two-dimensional face, etc. So it's kind of pasted in this way into the non-negative orthant. So something that's flat starts to get some structure. That. Okay, great. Okay, now let me just okay, so I wanted to do one thing which is actually quite well known, but it's sort of a nice enough statement to be interesting, but not so hard that I can't do it in 30 minutes. I can't just tell you everything about it in 30 minutes. It's along this theme of discretization. Okay, so here's a theorem. And I think this is the correct attribution, but I always feel like really nervous. I always feel really nervous about, but I think this goes back to this paper. This is a classical paper. So here's the theorem. Given any binary function, the vertices of the n cube the vertices of the n cube, different dimensions. There exists a sign neural network. So depth 2 means there's a single hidden layer that extends it. So, let me say what I mean by that. So, i.e. there exists an N1. And a theta in the parameter space of this signed neural network. Such that when you write down the corresponding function, so this is now a map that maps through this hidden layer and to n d, but here the depth is 2, d equals 2. So that this is a signed neural network. So here's the depth of the line. Okay. There's a signed neural network. And when you restrict f theta to the vertices of the n naught cube in the input space, it agrees with f. So this is some kind of discrete version of a universal representation theorem for this class of functions. So in other words, you, no matter what binary function you choose, you can represent it in this way. Very good. Okay, so let me sketch the proof first, and then let me give you details about it. And this will also introduce some concepts that will come up. So actually, I'm going to focus on ND equals 1, where the output dimension is 1, just because it's not so hard to increase the output dimension just by kind of stacking things up. I'll say more about that if I have time. But let's start with a focus on output dimension is 1. So we're just talking about binary functions from some higher dimensional binary space to 1-dimensional. So the way that I'm going to present this is, first of all, that any binary function represented what's called disjunctive normal form. And I'll explain what this form is. But the point is that there's some computational way of just representing, some standard computational way of representing any binary function. You know, you always can do it. Okay. So I'll put a pin in this. And then so actually I should say a little bit more though. Essentially, this disjunctive normal form is a composition of first ands and not ands, and then ors. So this is composition ands, not ands, ands, followed by ors. And then the second part of this, so the first part is kind of a classical representation theorem for binary functions. And then the second part is about implementing those classical binary functions using the structure of a sine neural network. So ands, not ands, and ors are all representable as single layer sine and ends. All right, so let me, so by the way, depth one sine and ends are also, I think, sometimes called linear threshold networks, or sorry, linear threshold functions. Or perceptrons. And the idea is that you're trying to make a yes/no decision. The idea is to take a bunch of inputs that are binary and weight them. And then if you're above a certain threshold, you say yes. And if you're below that threshold, you say no. That is nothing more than a depth one sine neural network. Okay. That's the sketch. Let me now let me give details. And actually the details are useful to kind of understanding what's going on. So let's actually start with the second part, because this is more to do with what we were talking about here.
So a sine neural network is the same as a neural network with an activation function with the step function.
Exactly. So let's start with the second part. So let's think about the and map. Start with and. So you might write this and it has these n inputs and they're all kind of treated symmetrically. This may also be written like that. And this is just +1. So the output of this is +1 if all of the inputs are +1 and -1 otherwise. And so let me just draw a picture. So I could write down some equations, or I could write down some parameters, but the picture is better. So the idea is that you want to construct a linear binary classifier that outputs 1 on this vertex of the unit cube, sorry, or the ±1 cube, and outputs 0 everywhere else, or sorry, -1 everywhere else. So what you're looking for is an affine hyperplane, a co-oriented affine hyperplane that separates the blue dots from the red dot. And of course, there is one, lots of them. Anything that kind of cuts off that vertex of the cube. Okay, and so this is the proof of that, and can be represented by a linear threshold network, or in other words, it can be represented as a one-layer sine neural network. And same thing with or, so maybe I don't need to write down these, but I will, just so you have it. So for or. Something's written like that. And this is just, again, it's, there's a color back there, I'm writing it. It's -1. Everything is negative. If all the inputs are -1, it's one otherwise. So again, it's the same sort of deal. You're cutting off a vertex of this Hamming cube. Or you can do that with a linear separator. And then let me point out also that if you have a function which is a bunch of ands and not ands, or sorry, ands and nots. That's not the same thing as NAND. Is NAND the same thing as and not, or is it something else? Okay, maybe I don't know, but I'll tell you what I mean here. So ands and nots. Okay, so now if you have any function which is which looks like so any string of ands and knots can also be viewed as a vertex of the Hamming cube. So for example, x1 and not x2 and not x3. So this is a symbol for not. The only input that outputs 1 is 1, -1, -1. Because should have written this down, but not of x1 of x is +1. If x1 is -1, -1. Okay, so any string like this is again just +1 on a single vertex of the Hamming cube, and so can be represented by so can be represented by a depth 1 sign and and in fact, if you think harder, I mean, well, there's people have studied this a lot, trying to understand which binary functions are represented by like a depth 1 relu, sorry, by a depth 1 sign NN. But what's clear is that if you have a face, any face of the Hamming cube, and it's +1 on that face, then you can do it with a linear cut. Okay, so this is the case where it's a 0 face and you're just cutting off that 0 face, but any lower dimensional face can also do it. Okay. So maybe I won't write that down because it's not going to be important for what I'm saying. So now let me give a definition slash lemma. And in the sketch of the proof, this is where I'm defining disjunctive normal form. So you can probably see where I'm going here. If you know disjunctive normal form already. So every binary function has a unique disjunctive normal form representation. Rather than like precisely defining disjunctive normal form, let me just explain how you find it. Because it's very, it's very natural. Okay, so how do you find disjunctive normal form? Well, first you find the set, which is the pre-image plus 1. So this is the set of all tuples that map to 1. In the case of those of ands and not, ands and nots and ors, that would be like the points that were colored red. Okay, so this is the set of vertices of the cube that get mapped to 1. So write the complete list. So this is the okay, and then associated to each element of this list, you have the natural string of ands and not ands that has the property that that string of ands and nots takes value 1 on that vertex and -1 everywhere else. Okay, so the second step is to write unique and not string. So for each n tuple, the pre-image of 1, write the unique and add not string. That outputs +1 on that tuple, -1 else. And then you just concatenate these and nots by ors. Let me give an example. And then it'll just be clear what you're doing. Example. So famous example. So with the function f equals x or, this is a function from binary 2 tuples to binary 1 tuples. And it takes value 1 on these two vertices, -1 on these two vertices. Okay, and it's clear you can't linearly separate the red from the blue. But you can write XOR in disjunctive normal form. So if you look at a preimage of 1 plus 1, this is just the set +1 + 1 -1 -1. The coordinates of the pink dots. And associated to each of these is a unique string of ands and and nots that output 1 only on that vertex. So in this case, it would be x1 and x2 outputs +1 just on this vertex. And not x1 and not x2 outputs +1 just on that vertex. And this disjunctive normal form, so you're saying, you're claiming, the claim is that XOR, x1, x2 is just, you take the OR of these two. So your output is +1 if you're either this or this or this. Okay, so it's a very kind of universal way of representing a binary function. You just list all the things that go to 1, and then you make sure that you have a function that just picks out that input, and then you just say, okay, you're +1 if you're this, or this. It's a very inefficient way of representing a binary function, but it always works. So let me just write it down so you have it in notes.
I'm a little confused by in what sense this is unique. Like, are we defining the definition?
Yeah.
Unique.
Okay, fair enough. So yeah, I guess unique up to reordering these and not statements.
Yeah, the horse is.
Um,
You'll see.
Well, if you're only allowing ands and and nots in the first step and the ors in the second step, I think it's unique up to just reordering the. You're saying inside here, reordering the ands and the
Inside in there,
yeah.
and then, yeah, the big step too.
Yeah. Anyway, point being, you always have this representation. And what that tells you is that you have this sort of logical circuit. Where here, y1 is this first. And 2 is second. And z is y1, y2. And then by what we argued with the linear thresholding pictures. Great plans. Or can be represented by a single layer sign neural network. Pop quiz. What's the width of the hidden layer in this construction?
Size of F inverse one.
Say it again.
Size of F inverse one.
Size of F inverse 1. Yeah, that's right. So you have one node in here for every and not and expression.
Will you talk about parity bit?
Say it again.
Will you talk about parity bit in this context?
Parity bit.
Like XOR is like a parity bit
Yeah.
in your example.
And
it's an incredibly important fundamental example because you see that you can have parity function leads to this exponentially large.
Right. Yes. So there's the parity function, and I guess that's kind of a worst case scenario for the size of this hidden layer. But yeah, I wasn't going to talk about it, but yeah, that's a really good point. Let's see. Okay, so since I have a few minutes, this actually was where I was gonna end, but looks like I went faster than I thought I would. So I'll just tell you what you do if you have multiple outputs. Well, you just kind of stack a bunch of these together. So the point is that ND is greater than 1. Then, yeah, basically you have a binary, you have this construction for each output node. And so you just have to here are the hidden nodes associated to the ands and and nots for this one. And then you just concatenate those with ors. Here are the ones for this one. But you still have the same logical circuit. You still are using the same idea for the logical circuit that basically have your original input neurons, and then you have this logical circuit for the binary function, which is the component, which is this component of the output, and you just stack them. So it's a product of these